Good morning, students. In the last lecture, we learned about the gravitational potential. What is the gravitational potential and what is the equation for the gravitational potential? Today, we are going to learn the applications of gravitational potential. And the first application is to find the gravitational potential outside a solid sphere. Okay, for that, consider a solid sphere of radius capital R, a solid sphere of radius capital R, and suppose the mass of the solid sphere is equal to capital M. Now, we know that what is the gravitational potential means. The gravitational potential is the amount of work done to bring the unit mass from infinity to the given point. Okay, so consider this point. We have to calculate the gravitational potential at this point due to this solid sphere having mass m. So consider that this solid sphere this solid sphere is divided into very large number of small shells. This solid sphere, it is divided into the large number of shells, each shell having mass m1. Okay, for the second the mass is m2, for the third it is m3. So we can say that this solid sphere is considered to be divided into the large number of cells having masses m1, m2, m3 up to mn. Okay, so what is the gravitational potential? What is the formula for the gravitational potential? The gravitational potential is denoted by letter V, and this V is equal to minus Gm divided by R. Okay, or we can, in the other way, we can say that this minus G into mass divided by a distance. Okay, so what is this mass? This is mass of each shell. So we can say that if we have to calculate the gravitational potential at point P, we have already considered that this solid sphere is divided into the large number of shells having mass m1, m2, m3 up to mn, and first of all we need to calculate the gravitational potential at point P due to shell m1, m2, m3, and then we are going to add all these gravitational potentials. Okay, so what is the gravitational potential due to shell having mass m1 and its distance from point P is considered as r? So we can write here, suppose the gravitational potential due to mass, a shell of mass m1 is v1, which is equal to minus g into m1 divided by r. Similarly, the gravitational potential due to a shell of mass m2, it is minus g m2 divided by r. Similarly, we can calculate the gravitational potential due to each cell having different masses. So, suppose V3 is equal to minus m3 divided by r. Okay, so if we need to calculate the gravitational potential, the total gravitational potential at point P due to whole solid sphere, then we must add this gravitational potential due to each individual cell having mass m1, m2, m3 up to mn. So what is the total gravitational potential V at the point P due to the solid sphere which is situated at a distance r from the center of the solid sphere. So this V is equal to V1 plus V2 plus V3 up to Vn. Okay, so what is V1? It is equal to minus G m1 divided by r plus minus G m2 upon r plus minus G mn divided by r. So we can say that what is the common in this? In this we get this minus G upon r common, and we can write here this m1 plus m2 plus mn. And what is this term? What this term indicate? This is the total mass of the solid. If we are dividing this solid sphere into the shells having mass m1, m2, m3 up to mn, if we add these masses, then we get the total mass of this solid sphere, which is denoted by letter capital M. So we can write here this minus G capital M divided by R. So this is the gravitational potential at a point outside a solid sphere. This is a solid sphere and this point P is like outside this solid sphere. So what is the gravitational potential at this point P? If this point P is situated at a distance r from the center of the solid sphere, then it is equal to minus Gm divided by r. As we see, this gravitational potential is inversely proportional to r. It is inversely proportional to r means as this distance or this point P is increases, as the distance increases from the center, the gravitational potential goes on decreasing. Okay, so this is the gravitational potential due to the solid sphere. Now, if we need to calculate the intensity of gravitational field, at point P, then we know that how the intensity of gravitational field can be calculated is E is equal to minus dV by dr. It is the derivative of gravitational potential with respect to distance. Okay, so therefore we can write here minus dvr of minus gm divided by r. So this minus minus get plus and this gm get common, so we can write it is dvr of 1 by r. And what is the derivative of 1 by r with respect to r, which is equal to gm divided by r square. So this is the intensity of electric field at point P. This is the intensity of electric field at point P when this point is situated outside a solid sphere. These two formulas, V is equal to minus Gm upon R and E is equal to Gm divided by R square. They are very useful to calculate the gravitational potential at a point which is situated outside a solid sphere. So today we discuss the gravitational potential, the applications of gravitational potential when this point P lies outside a solid sphere. In the next lecture, we are going to discuss another application, very important application, that when this point P is lie inside the solid sphere, then what is the gravitational potential and what is the intensity of gravitational field. So we are going to discuss the next application in the next lecture. So this is enough for today. Have a good day. Bye.